Hi Ruby, how are you? Hope you're doing fine. So what I'm showing here is a virtual machine, an Ubuntu virtual machine, and I have this Python, and we are now into temp folder. Inside this folder are two files. This is the smart contract that we are going to look now. It's written in Solidity. As can be seen by the extension Sol. It is just a text file and we can see the content of that. This is the content of the smart contract. It is just a text file. It looks like JavaScript. Now, let's try to dissect this particular smart contract. Obviously, it is a very small smart contract for pedagogic purposes. We're just going to understand how it works. Of course, an actual smart contracts is larger than this one. But nevertheless, this is the skeleton of a smart contract. It all begins with the keyword is contract. So this is a keyword of the Solidity, just like a class or in another language. But here it's the keyword is contract, and this one is the name of the contract. We can name it anything, but for this example, the name is incrementer. And we have open and close brackets. And then just like how it's done in JavaScript, there are member fields, and we can see that it has a number field, and the type is uint256, and this field is public. So without this public keyword, the number would be private, but since it is marked as public, then it is public. So there is a URL or Redux documentation of the exact um, how the structure of a smart contract, but it just looks like a JavaScript class where there's a class and there are member fields. They can be either public or private, and then there are member methods. The constructor is a special keyword, so it is the designated constructor of the incrementer, and the parameter that is passed to the constructor is used to set the initial value of the field number. And then we have a user-defined function called increment. So this is a specific method that the designer of the smart contract decided to have. He decided to like have the increment member method, and this particular method has a parameter, and then it is public, and then whatever is the being passed to the parameter is now being added to the member field number. So the name fits correctly that it is trying to increment number by this amount value. And now, so we can call increment to increment what is and the smart contract. This could be a token, but for now it's just an integer. And then there is another method called reset, and the purpose is just to reset the number back to zero again. So notice that both of these methods are public, meaning that they can be called. So these two methods are user defined. So you can define your own methods, whatever you like, just like how you define any member methods in JavaScript. The constructor is a special keyword. It is the designated constructor of the class when it is instantiated as an object. And I guess this is very obvious. This is just like JavaScript. Now, um, what else can I say here? So this pragma dictates the Solidity version on which the syntax of the smart contract here is is using. The version of Solidity is very much fast moving, so it is just same version style. Like anything that is, I think, 0.80 and up, or we can also lock it to a specific version. So this is just what it's telling us. Uh, some advanced newer Solidity version adds more verbs into the language. Like I don't know what those verbs are, but that's the idea. Uh, New features of Solidity adds additional keywords into the language, and perhaps you can use extra keywords can be useful in enhancing the security of a smart contract. While this tutorial is, I think, very old, so 0.8.0 is an old version. Well, it is what it is. I just copied this from the internet. So that's it. This is a smart contract. Now, the principle here is we still need to compile this smart contract. This can be compiled in a browser called the Remix. It is a browser-based IDE. I'm not very comfortable on using that. What instead I am very comfortable is the Python way of compiling a smart contract, and it is this Python code. So um, I am specifically using this Solidity compiler, SolCX, and then this is by the way Python, and the principle here is you just compile the smart contract here, and this is now the compiled file, which is a JSON, and then um, that JSON has two components: the application binary interface or ABI, and the smart contract hex bytes. Okay, these two components is important to understand because when you we deploy the bytecode, we send this to the blockchain, and this is what gets copied into the blockchain. This is the machine code, which is then gets interpreted by the Ethereum virtual machine, just like assembly language or whatever. However, when you are going to engage or interact to that smart contract, you need a stub like an API header or application binary interface that is the interface of what is being implemented in the bytecode. Okay, like in order to be able to call increment and reset, you have the client JavaScript has to have first a priori knowledge of what functions are callable, right? So those callable function signatures are defined here, not the implementation, just the signature of the function telling us that the smart contract has this method and that method. However, when you call it, the actual implementation that executes that call will be remote, not from your machine, but from the server, from the blockchain itself, from one of the nodes in the blockchain that won the proof of work. He will be the one responsible to execute the smart contract. Uh, that's it. We will exit now. But right now, since because of the dependency, I will have to install the I will have to install the Sol CX because right now we don't have it. Like for example, if I will do like that and I don't have it, I'll have to install it first. So let me install it right now. Um, but I don't want to pollute. I don't want to pollute my global Ubuntu namespace. So it's just like Node.js where there is a node modules directory and everything is there. So like neat and clean. There's also a way of doing that in Python, and that is uh, a virtual environment, Python 3, and it will create something like a Node.js node modules, which is this venv. And everything that I install from here will be inside the venv. I can delete the venv anytime, and I will just control C this, and I can be assured that my Ubuntu machine is back to clean condition, pristine clean. I don't want to pollute my Ubuntu, so everything is in the venv. And in fact, if we go to Python, you can see that the Python is pointing to the venv, so everything is localized now here. I'm going to install now the missing what is that, the this one, Sol CX, because we're going to need this to compile the smart contract. And the way to install that is this one. Okay, now it is installed. And if I type again to verify, and I no longer have an error. So I think it's about time now to compile the smart contract. Let's go back again to the Python that compiles this thing. We can see that we pass in the file name of the smart contract. Then it becomes this file. And then this file has two components, the ABI and the bytecode. And then we just print the two components to see what they look like. Okay. First, let's make a syntax error so that the smart contract will not compile. Just to play around, I will delete for example, like that. That's a wrong spelling that won't compile. Or maybe uh, maybe this one compile. I'll run the compiler now, and we can see that there is compile error. Okay, and we see the error somewhere here. And I will now fix the smart contract to make it compile there. Okay, clear the screen and compile it again. Now, all that I'm doing here in Python, compile.py, can be done in a browser called Remix. It is an IDE that is based on the browser and also is capable of compiling smart contract from the browser. But as I am a backend guy, I like to do everything from the backend. I will compile now, and compilation is successful. And this is the output of the two print commands that is inside a Python file. This is the ABI, or Application Binary Interface. This is what the client needs to have in order to engage or invoke remote calls into the smart contract. It will tell the client JavaScript or Web3 client JavaScript that the smart contract has the reset method. It has the what else? The increment method, and the rest are standard expected fields of a smart contract. But so far we can see that our custom methods are here, the increment and the reset. And because the client on JavaScript has an idea what are the available methods of the smart contract, which is, by the way, not in your machine, but remotely far into the blockchain, very far away, you will be able to still uh, invoke a call to that smart contract. Now, this is the separator of the two print command. This long hex here is the assembly language or machine code that contains the implementation body of the smart contract. So we can see the increment here and the reset. These are just stubs, have no implementation. These are just function definitions. The implementation of them are here, somewhere here. written in machine code. This hexadecimal will be loaded by the Ethereum virtual machine and will be executed there. Every step instruction in a smart contract, like you have a for loop, you have an if else, you increment something, anything that changes the state of the smart contract. What I mean by state is anything that changes the value of number. Maybe previously this is 0 and you call increment and now it is 1. So anything that changes the state, and we know that this is a state because this is a member variable. Anything that changes the state of this class smart contract requires gas fees. So one step is 0.001 is, another step is another 0.001. If you have a for loop, then if the for loop is 100 times, you multiply it by 100 times, and that will be the amount of gas that is consumed in order to execute your smart contract. So if the smart contract is long and lots of for loops, then the payment is also uh, bigger because every instruction line has a fee to execute. Now, the reason for this payment is not so that Vitalik will get rich. This is a compromise. To be honest, if the ancient problem has a solution, then this gas fee would not have been required. There's no physical law that really necessitates this gas fee. If the ancient problem had a solution, then we don't need gas fees. But as it turns out, there is an ancient problem in computer science called the halting problem. The halting problem, you can just Google that. Nobody has solved the halting problem. In summary, the halting problem is no computer program can know if a program will continue or stop. Because of that, Vitalik decided to design the smart contract to have a gas so that he can limit the execution of a contract. If he will not use a gas, anybody can do an infinite for loop and deploy it, and the blockchain will hang because a smart contract will not complete because it is an infinite for loop. But because every instruction has a gas, eventually the gas fees will be exhausted and the smart contract will stop to execute and return with an error. Okay, so it is a regulating principle so that you cannot hang up the blockchain. Again, the gas fees, there's no, it is just an accidental solution, incidental solution that needs to be there because of that unsolved computer science problem called the halting problem. And and that's it. Let us try to print what's the value of the TMP file. And let us just comment this. And you can see this is the, oh, it's not a JSON. Anyway, let us output the JSON. Okay, so it's not. Anyway, so that is, so from incrementer dot sol it becomes this file when it is compiled, and this file is compiled has two parts: the ABI application binary interface and the machine code to be executed by the Arturon virtual machine. Now in the Web3 client JavaScript, the sequence is the string, this string, let's comment again. This string you will use to You need a reference of this string, save it somewhere in your hard disk because you need that when you call to the smart contract later on, maybe in 1 week from now. So you need to save this into the hard drive. This one you need to deploy to the blockchain, and there are JavaScript Web3 client that can do this. But before deploying this, you need to sign it with your private key because only signed transactions are accepted by the blockchain. Of course, you also need to attach some amount of ETH tokens. We are not calling any methods yet during deployment. Okay, we are still deploying it, but not invoking any methods. But still, even at this initial stage of deployment, it already requires token so that it will be added into the transaction. And now this is one time only to deploy it. It will give you an address, a long hexadecimal address, and you can use that address to look into the Ethereum blockchain through the Scan Explorer, and you can see this very same hexadecimal there deployed in the browser, publicly visible for everyone. Then when you are about to call the smart contract because you save this into your hard disk, you're going to load it again and prepare your Web3 object in JavaScript, set up the ABI, attach a token. This time you have to attach another token because this one is for deployment. But when you call again, you have to attach a token, invoke the one of the methods, either increment or reset, and then that's the way how it works. So again, all of this can be done not in Python, but purely in JavaScript in the Remix browser. But but now it's clearer when it is here in the command line. By the way, the Python that this compile, it the actual guy that is responsible for compiling this when we install the dependencies actually here. This binary got created, Sol C compiler, and this binary is an executable Linux file. See, it is a 64-bit ELF. In fact, you can run it. See, there's even a help. Uh, yep. And this is the main guy responsible for compiling smart contract. The Python here is just a wrapper, but actually it depended on this binary guy, and this guy get installed when we did this installation in pip3. When we did this, it installed this binary executable, and when we call the Python, this is just a sugar coating, but eventually you can avoid Python. You can just use directly the binary. If you know the parameters, give it the you can just like sol cx, then give the incrementer JSON, something like that. And if you have the correct parameters, pass here, whatever, then eventually you will have the same output. So that's the principle. So I'm showing this because just to demystify everything. Um, because I don't like things when they are not very clearly known and who is who and who is the guy responsible for compilation and whether what part is sent over the blockchain and what part remains in your hard disk. So I hope this